Firstly, what exactly is lift and how is it created? Lift is a force produced by the dynamic effects of the air acting on an airfoil. We should also note that lift acts perpendicular to the flight path on the lateral axis, as well as to the centre of lift. Therefore, if a plane is in level flight, the direction of lift will be directly opposite the force of weight. But where is the lift actually produced on an aircraft? The force of lift is actually generated throughout the whole plane. However, it is mostly produced by the wings of the aircraft. When discussing lift, we usually refer to the cross-sectional shape of the wing, known as the airfoil or aerofoil. These certain properties make the design of an airfoil very effective at producing lift. The upper and lower surfaces of the airfoil are known as the cambers. You will notice that the upper camber is more pronounced than the lower camber, which appears to be relatively flat in comparison. The two extremities of the foil also differ in appearance. The rounded end, which faces forward in flight, is known as the leading edge. The sharper end is known as the trailing edge. These certain properties of the airfoil allow us to exploit the air's response to certain physical laws. We will now introduce ourselves to two theories of how lift is produced: Newton's theory of colliding particles and Bernoulli's theory of differential pressure. Firstly, we will examine Newton's explanation of lift, sometimes referred to as Newtonian lift. If we visualize air particles in the form of arrows colliding with the airfoil of an aircraft as it moves through the air, we will recognize that the particles striking the lower camber are deflected downwards. These particles moving towards the airfoil are known as the inflow. By changing the angle of attack, the amount of air being repelled downwards can also vary. As these particles are exerting a force on the airfoil and being repelled backwards, referred to as the outflow of particles, this must mean that the wing is being propelled upwards as according to Newton's third law, thus generating lift. This theory is known as the skipping stone theory. Unfortunately, it is not fully correct as it does not take into account the fact that both the upper and lower surface of a wing contribute to the turning of a flow of gas. A revised version of Newton's theory can more accurately describe the production of lift. As shown, the air particles are flowing above the upper camber of the airfoil, known as an upwash due to a natural phenomena known as the Coanda effect, also sometimes referred to as flow attachment. The air particles follow the contour of the airfoil. As the airfoil slopes downwards towards the trailing edge, the particles are forced downwards and this creates an effect called a downwash. The Coanda effect occurs because as a fluid moves across a surface, a certain amount of friction, called skin friction, occurs between the fluid and the surface, which tends to slow the moving fluid. If we refer back to Newton's third law, the downwash of the air particles will create an equal but opposite reaction on the wing of an aircraft, thus contributing to lift along with the lift created by the lower camber. The second theory is Bernoulli's principle. This principle states that as the velocity of the moving fluid increases, the pressure within the fluid decreases, thus explaining how the pressure of the moving fluid varies with its speed of motion. If we refer back to the shape of the aircraft's wing, the airfoil, we know that air is moving faster at the upper camber and slower at the lower camber. By applying Bernoulli's principle, we should realize that an area of lower pressure is being created above the wing, and an area of high pressure is being created below the wing. This is due to the shape of the airfoil. The upper camber's shape is curved, causing the air rushing over it to speed up and stretch out. Faster moving fluids create areas of lower pressure. The converse can be said about the lower camber. The air flowing below the wing moves in a straighter line, thus its speed and pressure remain about the same. The point where the pressure is the strongest and the velocity is practically zero is known as the stagnation point. Since high pressure always moves towards low pressure, the air below the wing pushes upwards towards the air above the wing, thus generating lift. The lift equation tells us how much lift will be produced under a given set of conditions. Firstly, we should acknowledge that lift depends on a number of complex dependencies, including the shape of the planform, the angle of attack, and the camber of the airfoil, to name a few. The lift equation was devised in order to characterize these dependencies by a single variable, the lift coefficient, denoted by CL. The lift equation is presented here. Rho represents air density. The greater the air density, the greater the lift produced. This is because there are more air molecules in denser areas, and so more molecules will be striking the airfoil. The true airspeed of the aircraft is denoted by V. By grouping P and V in brackets, their product is known as dynamic pressure. Pressure, as we know, is measured in force per unit area. Therefore, if we multiply the dynamic pressure by the area of the wing, S, we will obtain the force generated in newtons. Thus, we can then calculate the force required for a successful flight.